Okay, so 3D modeling is the topic of today's lesson. And so unlike the grid that we made last time, or the quad that we started out with, right, which were both 2D, now we've got a whole other dimension to play with in this lesson. And so the first 3D model that we'll make will be a tube. And we'll have like a base shape, which is a circle on the XZ plane, and we'll extrude that along a path that will travel kind of upwards in the y-axis. And so we'll end up with something like this, where our outer surface of this tube will be a 3D model. And so that's the first 3D model we'll make. I think by the end of this lesson, we may make some other stuff with this as sort of a starting point. But you may be thinking like, well, in the last lesson, we made just a two-dimensional grid, but the fact that it was procedural, it was already pretty complex, especially the part where we connected the dots, where we created the triangles. So is this going to be even more complex in 3D? You'd think so, but I actually think what we'll do today will be a little bit simpler than what we did last time. So that's kind of a little tease for what I'm going to talk about a little bit later. But first, let me say how we'll make this 3D model. And I'll introduce a new concept here, sort of new. We actually have seen this already. I just didn't sort of name it. But we'll use parametric functions as we create our 3D model. Now, again, that might sound complex, right? There's a lot of syllables going on here, parametric functions. But basically what this means is that we're going to have some kind of input parameter, and that's going to range from 0 to 1, or 0% to 100%, and that parametric function will map that parameter to some output that's a unique output depending on whatever parameter you're feeding in, okay? And so an example that we've seen already that you could think of as being a parametric function could be this lerp function, or linear interpolate, that we saw in our shader lesson. So that takes one value, we can call it value A, and a second value, value B. Let me move this over so we get a little bit more space. And then the third thing that we passed into this was a parameter. And so you could call this blend T. And this T here is just one of my conventions. I call basically any parameter that goes from 0 to 1 and controls where we are, like in this example, in this blend from A to B. I usually will just call a single parameter like that T. So in this case, let's say blend T is 0.75. We'll be 75% of the way through this blend. So that's the basic idea of what a parametric function is. A very closely related concept to that we'll use in our 3D models is the idea of having parametric coordinates. And again, even more syllables maybe this time. But all it really means is that we'll have two parameters instead of one. And so if we call our single parameter t, we can call our parametric coordinates u and v. And so this is kind of sounding familiar to what we did in the last lesson, right? And these will, again, range from 0 to 1 or 0 to 100%. And so we'll use these two coordinates in order to tell us where we are in this mesh. We'll use our u coordinate, and maybe I'll put these in colors here so u can be red. And so this is just going to control where we are on that base shape that gets extruded sort of from 0 to 100% of the way through that shape. And then our v parameter will tell us where we are on that path along which we're extruding the base shape. So that's going to, again, start at 0% and then go all the way up to 100%. So even though we're making a 3D model, because of the fact that we're modeling this using parametric coordinates, we can still just think about this in terms of two dimensions. So basically, any combination of our u parameter and our v parameter will point to sort of a unique position on this 3D surface that we're going to create. All right, so now we just need to come up with some kind of conversion from this UV parametric space into our XYZ sort of 3D space so that we can actually put those 3D points into our vertex buffer. So let's do that now. And really what we're doing here is creating that parametric function, this time not for a single parameter, but for the parametric coordinates. We'll map our UV coordinates to some position on our 3D surface. And we'll start with why this is the most simple one, is that this will be driven by our v coordinate. And we can say that this tube, we want it to start sort of at 0, like the floor plane, and then we want it to sort of get extruded up to some height that we can configure on this thing, okay? So this will actually work exactly the same way as when we gave our grid a height at the end of that last lesson. We'll just say that our y is v times height, okay? And let's just throw the colors for v on here just so we can keep track of that. Now for our x and z coordinates, those will be determined by our base shape, our circle, which is driven by our u parameter, right? Now, this is where we're going to start getting into some sort of shock and awe math type stuff. So hopefully you don't freak out. I'm going to kind of front load the sort of crazy part of it. I'm just going to write these all down, but I think in a few minutes you should understand pretty much everything that I'm about to write here. So let's start with z. This will be sine, so a sine wave of 2 pi, another math term here, times u. And then we'll actually also probably want to multiply in some radius so we can configure our x and z as well as our y. And the radius of the tube is basically just saying what is this distance from the center of the tube out to the outer edge. Okay, and then we can say for our x, this is actually going to be the exact same thing, except that we'll take our sine here and replace it with a cosine. Okay, so does that help that we're introducing another math term? Well, actually, it's not that bad. You'll see it's basically the exact same thing as sine. So you could just kind of leave it at this and say, that's the equation for our tube. Let's go. I think it is worthwhile looking at how exactly this sine wave works, though, because this is one of the really foundational elements to our toolkit here. And I think if you have an understanding at more of an intuitive or basic level of what this sine wave is doing, and what the meaning of this 2 pi is, etc., it will really come in handy in the future lessons, especially as we start looking at animation in our second unit of the course. So let's learn a little bit more about how sine and cosine work. And even if you learn about these in school, maybe this will kind of simplify it and make it easier to remember. So I'm just going to start drawing, and both sine and cosine are these repeating wave patterns that go off into infinity as we kind of step forward in this input axis. And this is our output axis. And these 3 lines that I drew correspond to values of 1 at the top, 0 in the middle, and -1 at the bottom. Okay, and so then here is our input axis, and I'll hold off on labeling this fully, but for now I'll just say that 0 is our starting value. Now, both of these waves, sine and cosine, will move from checkpoint to checkpoint is the way that I like to think about it. And so for each of these waves, we've got 4 checkpoints, and then they'll repeat. So let's look at our sine wave first. It's going to start at 0, 0. And then the next checkpoint is going to be at 1. Then it's going to come back down to 0. Then it's going to move down to -1. And then it's going to come back up to 0. So here it repeats the wave pattern. So it'll come up here, come back down here. But these are really the 4 different checkpoints here. And then it comes back to the first checkpoint. So what makes this the sine wave, instead of just a bunch of random lines, is that when you draw the values between the checkpoints, you get perfect circular arcs, right? Especially if you're not working with like this misshapen drawing, right? Now for cosine, this is going to be basically the exact same thing as sine, as I just mentioned. The only difference is we shift these checkpoints over by 1 checkpoint. So this will be where we start. For cosine, we start at 1 with the input at 0. Then we'll go down to a 0. Then we'll go down to -1. Back up to 0, and then we'll come back to where we started, which is 1, and then we just kind of repeat from there. So this just, again, works the exact same way as sine. We still have these perfect circular arcs. We're just offset kind of by 1 checkpoint for cosine. And now, as we mentioned, right, here's the location where both of these patterns repeat, and the sort of final piece of this is that the value of the input axis where these repeat is going to be 2 pi. So 2 pi is the period of both sine and cosine, or the duration of the pattern kind of before it repeats. Now, why 2 pi? Why not some other value? That gets kind of into like metaphysics or some other kind of topic altogether. So interesting, but on a practical level, the meaning of all this is that as our u goes from 0 to 1, we're multiplying that by 2 pi, and that's going to drive us through like a full cycle of both of our waves here. And let's just visualize how does this actually turn into a circle quickly. Let's just chart out the x and z components of our parametric function where we use these waves. So this will be x here, and this will be z going up. So we'll look at this kind of from a top-down perspective. And remember, cosine is going to be our x value, and z will be sine. So if we look at this, our cosine is at 1 to start, and our sine is at 0. So that's going to be 1, 0. For our starting value. And so then we'll move to 0 for cosine and 1 for sine. So that's going to put us here. And then we'll move to -1 for cosine and 0 for sine. So that's going to put us here. And you could probably guess our final point before we repeat will be back at 0 for our cosine, and we'll be at -1 for sine. So that will put us there. And then again, the magic of these functions, we get a perfect circle by connecting these up. So all the distances from the edge to the center will be the exact same distance. And in this case, that distance is 1. So this is called the unit circle. And then by multiplying our tube's radius into that, we'll kind of get the value that we want. So that's how we're going to create our tube. And at this point, you might be wondering, well, we spent all this time talking about what's going to go into that vertex buffer. What about the index buffer, right? How are we going to connect these dots? That's the hardest part of this whole thing, right? So now is the time for the big reveal here. If you just zoom in and look at some tiny slice of the tube, and we start drawing some points on this that we want to connect. So we'll draw points like that, and we can make some points in the middle. All right, and then we start connecting the dots. Maybe you'll start seeing where I'm going here, is that if you zoom in on this, it looks identical to a grid. It is a grid. And so we can use the exact same triangulation pattern that we created in our grid lesson last time for our tube. So you can think about our tube as being a series of circles that we're extruding along this path, or you can think about it as our grid that we're kind of wrapping around this parametric function. But either way, that's how we're going to create our 3D model. And so let's get to work. So I've got an empty tube script that I set up here. And as I was just saying, this is going to be heavily based on our grid. So let's just copy that over to our tube and just make sure that we rename this so that it still is called tube. All right. And so for the first thing I want to do here is let's just take this parametric function and let's translate that to code. So it's going to take u and v as its inputs, right? And then it will output like a vertex position that we'll put into our vertex buffer. Okay, so this is going to return a vector 3, and we can call it vertex position. And it will take as its inputs u and v parametric coordinates, okay? And then we can just basically just copy this, right? Our x coordinate will be cosine, and so that's going to be in our math F class here. And then we'll take also for math F pi multiply by 2, multiply our u in there. And then we need to multiply in our radius. Now the grid that we just copied has a width. So let's change this to radius. And we'll use that to multiply into our x coordinate. Okay, so now we've got x. And for our z, let's just do that next because we just need to change this to sine. All right, so z is done. Now for y, we just need to say that's going to be v times height. And now height we are going to be able to reuse from the grid. And then this is still complaining because we just need to now return a new vector 3 with x, y, and z as its 3 components. All right, so that's our vertex position function. And if we scroll down to where we're building the mesh, let's see where we want to use that. So here we can see this is complaining our x value no longer works because we don't have a width. Well, that's okay because we don't really want to use this x value anyway. We've got our new whole position defined up here in our parametric function. So let's actually take this y, which is, I mean, this is actually correct for the y, but we already have that logic elsewhere now. So let's take both of these away. And in here where we're adding our vertex to our vertex buffer, let's just invoke our vertex position function with our u and v coordinates that we already have from our grid. And that's kind of it for the tube script. Now, I think we could come in here and say like, well, we don't really have rows, right? We want to have kind of like subdivisions of our v parameter instead of rows. That's kind of more grid specific. And then same with columns, right? That's kind of more like we're subdividing along our u parameter. So I don't know if that's more or less clear, but I think it's more accurate to say this is going to be our v subdivisions, and this will be our u subdivisions. Right, and then we could just kind of do the same thing here. We could call this like maybe v iteration or v iter. We could rename this to u iter, right? But this is just kind of, we're just kind of fiddling around, right? We already have the whole tube script now. And actually, speaking of minor changes, I kind of want to have u come before v. But all right, let's test this out. So I've got a tube scene set up already with our tube script on it. So let's just give this, let's say 8 subdivisions each on u and v. And we can say our radius will be 1 and height will be 4. So it's going to be kind of like a taller tube than it is wide. Let's build a mesh. And so we've got our tube. So I think that was not only a little bit simpler than what we did for the grid, I think it was a lot simpler because we put in all that elbow grease as we were making our grid And now we're sort of reaping the benefits of having made that grid with its procedural design. So now we can kind of play around with these different values here. Let's see what it looks like with a radius of 2. Okay, and then we could increase this height so that it will be kind of back to the proportions it had before, right? Or maybe we want it to come back and it'll be sort of a squatter tube. And we do have a missing cap here, but that's okay. We'll actually get to that in a second. But this is kind of blocky, right? You can see the sort of different U subdivisions very clearly here. And so if we want to increase those, let's say to 16, let's see, we should see something that's a little bit more sort of circular. And then we can go further with that to 32 maybe. And so by doing that, we're getting more samples of our parametric function and kind of filling out that circle shape that we're creating with our sine and cosine waves. And then we can also change the number of V subdivisions. Now this is not really going to change the shape of the mesh, but it will add sort of more triangles as we step through our V parameter. And so now one thing I do want to highlight before we move on is that if you reduce the number of U subdivisions to a very small number, let's say 4, so this should be like a box or a rectangle shape, right? So if we build the mesh, you can see it doesn't really look like a box or a rectangle. It looks more like a triangle. And if we go down to 3, where we would expect to see the triangle, that's just going to give us something more like a quad with 2 sides. So what's going on there? This is actually a result of the fact that our circle loops all the way back around on itself, right? Whereas the grid does not. So if we're folding the grid around this circle, this is kind of an artifact of creating our triangulation pattern the way we did. And so maybe we'll look at this further in a bonus lesson, but for now we've got a perfectly functional tube. So let's just go forward with this. And now I did promise at the start of this lesson that we would not just be making a tube. And so one simple way we can do this is to change these values that we're getting out of this parametric function output from our same input. We can get a different shape than just this tube. And so what I have in mind for that is, let me just paste this in. This is a drawing that I kind of made off screen, and it's a chess piece, it's a pawn. And so what we can do is we can take our tube, and as we sort of extrude along this V coordinate, which will look like this, right, on our pawn, we can just take this radius and change it depending on what the V coordinate is. And so we can kind of sculpt this and get the silhouette of our pawn from this sort of base shape of the tube. And so there's many different ways that you could do this. You can layer some math functions kind of on top of each other. And we might do stuff like that a little bit later in the course, actually. But for now, let's just use an animation curve, which is kind of a Unity built-in tool. And I think this is a pretty useful tool to just get something up and running pretty quickly, so we can kind of change the shape and see what happens. So we can call this our radius curve, let's say. And we can create, like, let's say a curve radius multiplier by taking this curve and evaluating it, here we go, with our V parameter. So as V kind of goes from 0 to 1, we'll evaluate 100% of this curve, get our radius multiplier as the output here. So this is another little parametric function. And then we can use that to get our, let's say, like our radius at this particular position of V. Okay, so that would be our global radius times this curve radius multiplier. And then we'll use this sort of local radius to multiply into our x and z coordinates rather than our global radius. Okay, so let's test this out. Let's come back here and let's just put some random curve on this just to see if it works. We'll rebuild the mesh. And so, yep, now we've got our parametric function and it's now being controlled by this radius curve. And so now let's just create that pawn shape. And so I'll paste that drawing in again. I'm going to scale this up a little bit this time. And I can rotate this as well. And so what I'm doing here is I'm trying to create the shape that this is going to look like when it's in this animation curve tool. And so this is going to give us the sort of radius multiplier that we want as we step through our V parameter, which is now sort of going left to right here. And so as we step forward through V, we'll kind of step through our radius curve. Okay, so let's pull this up, and I'm going to just initialize this, which is going to give us a straight line at 1. So if we rebuild this, our tube should go back to normal, right? And the first change I'll make here is I'll create a point in the middle, and then I'll move these endpoints down to 0 as the output values. And what that will accomplish is if we rebuild this, you'll see that the top and bottom of this tube are now closed off. Okay, and that's also going to tell us that this line here that I drew sort of in the middle of the pawn, if our sort of radius touches that, then we know that our radius multiplier will be 0 at that location. Okay, so now let's just kind of start playing around with these points and see if we can get something that looks kind of like a pawn. And if you're not using Unity as your environment to try these concepts out as you're going through this course, you can look at Catmull-ROM splines if you're interested in trying to create your own tool, or you could also use math functions to do this. This is really just more trying to show you how customizable the parametric modeling can be. Okay, so let's just see what that looks like. Let's rebuild the mesh. And I think it looks decent. We can reduce the radius down to 1. And so I think that looks kind of like a pawn. What I'm going to do now is I'll just keep fiddling with this for a little bit, and then I'll come back when I've got something to show you. Okay, so I've come up with something that I think looks pretty good. You may have to tell me what you think, but let's see what this looks like. So this obviously does not look like a pawn, but we only have 4 subdivisions in V right now. And so changing the number of V subdivisions will actually change our shape now, because as we move through V, we're changing the radius, right? So if I increase this, let's just start doubling this. So let's go up to 8. And that's starting to look a little bit like a pawn, I guess. Let's go to 16. Okay, that's definitely starting to look more pawn-like. 32. And so this will become kind of more and more rounded as we go up here. And so what we've done in this lesson is we've taken our grid, turned that into a 3D tube, and now we've taken that into its own sort of parametric modeling system almost. So now we've got this unlit pawn here. In the next lesson, let's go back to the shader side of things and let's start adding some light to our scene.